Credentials become valuable when holders can use them. In this section, the wallet becomes the trusted bridge, storing credentials securely, helping the user choose what to share, and presenting proof to a verifier with consent and privacy. You've already built the foundation: identity models, verifiable credentials, DIDs, cryptographic proofs, and issuer implementation. Now the focus moves to the holder, where credentials are received, protected, and later presented in a controlled way. The holder sits between receiving a credential and proving something with it. An issuer provides a verifiable credential, the holder stores it in a wallet, and later chooses what to present to a verifier. That holder might be a person, an enterprise system, a device, or an agent. The central idea is consent and control. Share the full credential, selected claims, or a privacy-preserving proof, depending on the situation. From the holder's perspective, a wallet is not just a container. It supports the credential lifecycle. A credential may arrive through a QR code, deep link, API, or wallet protocol. Before storing it, the wallet should verify the issuer signature and confirm the credential matches an expected schema. After that, the holder needs ways to organize it, update it, export it, use it in presentations, and remove it when it is no longer needed. Wallet architecture is really a decision about where trust lives. Mobile wallets keep keys close to the user, often protected by biometrics and secure hardware, and work well with QR codes or deep links. Browser wallets fit web-native flows but depend heavily on extension or app security. Server-side wallets support enterprises, automation, and custodial recovery, but shift control toward the operator. Each choice affects privacy, integration, and risk. The core question is key control. In a non-custodial wallet, users get maximum autonomy and privacy, but they must handle backup, recovery, and loss scenarios correctly. In a custodial wallet, recovery and onboarding are easier, but users must trust a provider, creating compliance, liability, and breach risk. Hybrid designs try to balance these trade-offs through social recovery, cloud-wrapped keys, hardware keys, or managed agents. Think of a wallet as a small trust system, not just a file cabinet. The credential store keeps credentials, issuer details, status, and display data. Key management protects signing and encryption keys, including rotation. A resolver checks identifiers. The presentation engine turns selected credentials into proofs for verifier requests. Protocol handling manages message exchange, while policy and consent controls help ensure the user approves exactly what is shared. Secure wallet storage starts with a simple assumption. Storage may be exposed through a lost device, compromised browser profile, or database leak. Credential payloads should be encrypted before they are written anywhere, using authenticated encryption such as AES GCM or trusted platform storage that manages keys safely. Metadata matters too. Avoid plaintext details that reveal identity, credential type, or usage patterns. Where possible, separate credentials, wallet records, indexes, and audit logs so one compromise does not expose the full picture. Wallet keys are the root of trust, so their lifecycle is a security boundary. Generate keys with trusted platform APIs or audited cryptography. Then keep raw private keys inside hardware-backed or OS-protected storage whenever possible. Unlocking should require user presence, such as biometrics, a PIN, passkey, or device unlock. Recovery is the hard trade-off. Backups prevent lockout, but every recovery path can become an attack path. Encrypt recovery material, limit access, and avoid exposing raw keys. Before a wallet can prove anything, it must safely receive the credential. The process usually starts with an offer, such as a QR code, deep link, email link, API callback, or embedded web flow. The holder accepts, and the issuer may require authentication. Once delivered, the wallet validates the credential's signature, issuer, schema, and expiration. Only then should it store the credential, along with display details like issuer name and credential type. A presentation request is the verifier's way of asking for proof with rules attached. It can specify the credential type, acceptable issuers, schema, expiry, status, and the particular claims or predicates needed. The wallet checks those constraints, including a fresh nonce or challenge, so an old response cannot be replayed. Then it translates the request into plain language for the holder. Consent should happen before the wallet creates the presentation response. When a verifier asks for proof, the wallet should not simply pick the first credential it finds. It compares each candidate against the request: type, issuer, schema, subject, expiry, and revocation status. Then it can filter or rank the results, showing which credentials qualify and why others fail. If several work, the user chooses. Even then, the wallet should disclose only the required claims, not every attribute inside the credential. After selecting the right credentials, the wallet must decide how much information to expose. A standard presentation may send the full credential plus a holder binding proof. Selective disclosure narrows that to only the required claims. With zero-knowledge proofs, the wallet can prove a statement, like over 18, without revealing the birth date. In every case, the verifier still needs enough evidence to check the challenge, issuer trust, and credential status. A consent screen is more than a confirmation dialog. It is a security boundary. Before creating a presentation, the user should know who is asking, what proof is requested, why it is needed, and what data will leave the wallet. Good defaults minimize disclosure, separate required from optional claims, and flag sensitive attributes. Warnings should use plain language, especially for unknown verifiers, expired credentials, or requests that ask for more than the purpose requires. Wallets are the holder's control point. They store credentials securely, manage keys, minimize metadata, and turn verifier requests into consent-based proofs. Architecture choices shape privacy, recovery, custody, and trust. Next, we move to the verifier side, requesting credentials, validating proofs, checking trust, and making authorization decisions.